Hi, welcome to Math Extra. This is Saritha. Today our topic is internal angular bisector and incenter. So first we will know what is an angular bisector. So in the yesterday class we have seen perpendicular bisector. In that bisector is nothing but anything is dividing into two equal parts. But here angular bisector means the line which is dividing the angle into two equal parts. See, this is a triangle. These ABC are vertices of a triangle. So this is a angle A. So this angle is dividing into two equal parts. X degrees, X degrees. Whatever may be the angle, so that angle, this line is dividing that angle into two equal parts. This we call it as an angular bisector. So what is an internal angular bisector? As this line is dividing the internal angles of a triangle. See, this angle A is an internal angle. Angle B is also another internal angle. Angle C is also another internal angle. So, these three internal angles, the lines which are dividing these three internal angles into two equal parts. That is why these lines are called internal angular bisectors. Okay, so how many internal angular bisectors are possible? See, as there are three internal angles are present in a triangle, so there are three internal angular bisectors are possible. So what happens if you draw all the internal angular bisectors in one triangle? So these three lines are concurrent at one point, isn't it? This is one internal angular bisector. This is one internal angular bisector. This is another internal angular bisector. These three internal angular bisectors are concurrent at this point. So this point of concurrency, we call it as an incenter. So what is an incenter? It is nothing but point of concurrency of internal angular bisectors. Okay. So this we denote with the capital I, isn't it? I is denoting for incenter. Okay. So if you take an other type of triangle, okay, this is an acute angle triangle. Now I am considering an obtuse angle triangle. See this angle, okay, this line is dividing this angle into two equal parts, x degrees, x degrees. Okay. So this angle is again dividing two equal parts, y degrees, y degrees. This angle is dividing two equal parts, z degrees, z degrees. Okay. What happens? These three internal angular bisectors are also concurrent at this point. So this we call it as an incenter. See, you observe in the case of acute angle triangle and obtuse angle triangle, what happens? This incenter is present internally. See, for an acute angle triangle, where is the location of incenter? It is interior of a triangle. When you come to an obtuse angle triangle, what happens? Here also the incenter lies inside the triangle only. So if you consider right angle triangle also, see this is a right angle triangle. This is one internal angular bisector. This is another internal angular bisector. This is another internal bisector. So here also the incenter lies inside the triangle. Means in all the three cases, the incenter lies in interior of a triangle. So you observe this point. So in the case of centroid, we have seen that centroid is always an interior point of a triangle. So similarly, this incenter is also always an interior point of a triangle. This is the one property of incenter. Okay, this incenter always lies in interior of a triangle. Okay, next. So properties of incenter. Okay, so the first property is is nothing but the incenter lies always interior of a triangle. So whatever the type of triangle it may be, so the incenter is always interior. Okay. So the second property is, see, if you take this triangle, so let us consider the side opposite to capital A angle is small a, and the side opposite to capital B vertex is small b, and the side opposite to capital C is small c. Okay. So this is the internal angular bisector. Okay. Let us draw one more triangle. See. So this is an angular bisector of through vertex A. Okay. This is B, this is side C, and this, okay, this is AD, internal angular bisector. Okay. So it is dividing into two equal parts. So somewhere here incenter present. Okay. Somewhere here incenter present. So how this internal angular bisector, AD is nothing but internal angular bisector, right? So how this internal angular bisector divides this BC side in the ratio of the remaining two sides. If this is C, so this BD is C, and if this is B, so this DC is B, which is nothing but BD is to DC, which is equal to C is to B. See, this internal angular bisector divide the opposite side in the ratio of remaining two sides, isn't it? See, if you know these two sides, you can easily find out the other side. Whether it may be any type of triangle, we don't care that. So, what we need to do, we should know the two sides. Then, if they ask for the which ratio the internal angular bisector divide the third side, then you can answer easily by the remaining two sides, because this internal angular bisector divide the third side in the ratio of the remaining two sides. Okay, which is nothing but C is to B. Similarly, so if BE internal angular bisector, if this is BE internal angular bisector, divide this side in the ratio of these two sides, isn't it? So then if this is one more internal angular bisector, this again divide this side in the ratio of the remaining two sides. Okay. So this way the internal angular bisector divides the third side in the ratio of remaining two sides. Okay. So this is the second property. So our next property is, this is a triangle ABC. So this is an internal angular bisector. Okay. So AD is an internal angular bisector. Suppose this is the incenter I. Okay. So this center is nothing but it is formed by the concurrency of all the three internal angular bisectors. Okay. So sometimes he may ask this incenter divide this internal angular bisector in what ratio. So he may ask the question that this incenter divide the internal angular bisectors in what ratio. So that time this property is very helpful. See, this is a side A, because it is, this side is opposite to vertex A, angle A, and this side is opposite to angle B. Okay. So this is small b, and this side is opposite to small c. Sorry, angle C. So this is small c. Okay. So now this incenter divide this internal angular bisector in the ratio of sum of these two sides, that is B plus C is to, and this is the other side A, which is nothing but AI is to ID, which is equal to B plus C is to A. So did you understand? So this incenter divide the internal angular bisector in the ratio of sum of the two sides. These two sides are either side of the internal angular bisector, isn't it? Sum of these two sides and the other side. That is nothing but B plus C is to A. So similarly, the internal angular bisector through vertex B, so that also divide the incenter divide that internal angular bisector is also in the ratio of sum of the two sides and the other side. Okay. So from this you can easily find out, if you know the sides of a triangle, then you can easily find out the in which ratio the incenter divide the internal angular bisectors. It is nothing but similar to in the centroid. What happens? The centroid divide the median in the ratio of 2:1 from the vertex, right? So similarly, this incenter divide this internal angular bisector in the ratio of sum of the two sides and other side through the vertex. Okay, from the vertex. The next property is, see, you take one triangle. If you draw a circle which touches all the three sides of a triangle. Okay. So let us consider this is a triangle and it touches all the three sides of a triangle. Okay. So this is triangle ABC. Okay. This is the circle. Okay. This is incenter. Okay. This is the angular bisector. This is the incenter I. This incenter I is also center of this triangle. So as this circle is touching all the three sides of a triangle, we call this circle as a incircle. Okay. So this incenter is nothing but center of this circle. Okay. So from all the sides to the internal incenter, from all the sides to the incenter, the distance is constant. This distance we call it as a radius, and as this is a in circle, this radius we call it as a in radius. Okay. So in radius is always represented by a small r. There we have seen circumradius is represented by capital R, in radius is represented with small r. Okay. Now we'll define what is small r. So in order to calculate in radius for different types of triangles, we have formula that is r is equal to delta by s. So what is delta here? Delta is nothing but the area of a triangle. So the with whatever the triangle you consider, so the area of the triangle is represented by a delta. And this S is nothing but semi-perimeter of a triangle. See, if the triangle has all the three sides, right? So, what is semi-perimeter? S is nothing but A plus B plus C by 2. If A plus A, B, C are sides of a triangle, then A plus B plus C by 2 is nothing but semi-perimeter of a triangle. So, if we know area and all the three sides of a triangle, then we will easily find out in radius of a triangle. This is for all type of triangles. See, if you, and what is the in radius for equilateral triangle? See, in the case of equilateral triangle, you know the area of equilateral triangle is nothing but root 3 by 4a square. And we know all the three sides are equal in equilateral triangle, right? A is equal to B is equal to C. A is equal to B is equal to C. Then what will be the semi-perimeter? So 3a by 2 is the semi-perimeter. If you substitute this area and semi-perimeter of a triangle in this formula, you can easily find out that in radius r is equal to a by root 3. This is for equilateral triangle. This is in radius for equilateral triangle. So this is the in radius for equilateral triangle. If you consider right angle triangle, so what is the in radius for that? R is equal to sum of the perpendicular sides. If A and B are sum of the perpendicular sides and C is the hypotenuse, then sum of the perpendicular sides minus hypotenuse by 2 is the in radius for right angle triangle. So you have to remember this is for all type of triangles and this is for equilateral triangle and this is for right angle triangle. Okay, and for equilateral triangle there is a relation between the circumradius and inradius. So for equilateral triangles the circumradius is always equal to 2 times of inradius. This is only for equilateral triangle. Okay, and in general we have an Euler's inequality, that is always circumradius. This capital R is always greater than or equal to 2R. It should not be less than 2R. It always should be greater than or equal to 2R. It is equality holds whenever we consider equilateral triangle. In other cases, it is always greater than 2R only. So, this is the Euler's inequality in the case of circumradius and inradius. Okay, we can find length of the internal angular bisectors. We have seen a formula to find out length of the median in the case of centroid medians. Okay, so similarly we can also find out length of the internal angular bisector. If this AD is a internal angular bisector, so we can sometimes they may ask to find the length of the internal angular bisector. That time we need a formula to find out length of this. So what is the formula to find out the internal angular bisector's length? So which is nothing but AD is equal to 2 by the sum of these two sides. These two sides are either side of the internal angular bisector, right? So which is nothing but B plus C into under root of B into C into S minus A, where this A is nothing but the side opposite to angle A. Okay, so this S is nothing but semi-perimeter of a triangle, which is nothing but A plus B plus C by 2. Okay, so this by this formula we can find out the length of the internal angular bisector, that is AD length. And similarly you can find length of BE and you can also find out length of CF. So these are other internal angular bisectors. See what is BE? BE is equal to, so the sides of either side of the internal angular bisector BE. So what are the sides? A and C, right? So you have to take sum of those two. 2 by A plus C under root of A into C into S minus B. So this side is exactly opposite to angle B. CF length. Similarly, you can write CF. CF, the sides which are either side of the CF are B and A, right? So 2 by A plus B into under root of A into B into S minus C. So in this way we can calculate all the lengths of the internal angular bisectors. And we have one more property, that is triangle ABI, right? This ABI and this is the side C. Okay, and this the side B and this triangle is AIC. Okay, so and this triangle is BIC and this side is A. So these areas, the triangle areas which are nothing but triangle BIA. You observe triangle BIA is to triangle AIC, which is nothing is to triangle BIC. So these three are in the ratio of their corresponding sides. See, this is the side corresponding to this triangle, right? So this ratio is corresponding to their side. So BIA, the corresponding side is C, right? C is 2. And AIC, so the corresponding side is B is 2. And BIC, the corresponding side is A. So this areas ratio is always in the ratio of their corresponding sides. Okay, this is one more property related to in-center. We have a relation for we have seen one relation for orthocenter, nothing but this angle A and the angle formed by this side at the orthocenter are always supplementary to each other. Nothing but angle A plus angle BOC is equal to 180 degrees. This is the relation in case of orthocenter. Okay, so X is nothing but circumcenter. Okay, so here what is the relation? So always this B, the angle formed by this side at the circumcenter is always twice the angle of A. Okay, so which is nothing but angle BSC, which is equal to twice of angle A. Okay, and in the case of in-center, this I is for in-center, right? So what is the relation for in-center? The angle formed by this side at the in-center is always equal to this angle BIC, which is always equal to 90 plus angle A by 2. Okay, so these three relations are very important. We have to observe whether this angle is formed at the orthocenter, or this angle is formed at the circumcenter, or this angle is formed at the in-center. So by depending on that only, we have to decide whether there is this relation is applicable, or this relation is applicable, or this relation is applicable. This is for orthocenter, these two are supplementary, and this is for circumcenter, that is this angle is twice of that angle, and this is for in-center, which is nothing but 90 plus angle A by 2. Okay,